Okay, there we go. Shelly, do people have keys?
I think some people have keys, and some people may not have keys.
Okay.
So if you ever got a key from us, right, you can use it. If not, maybe Aparna, you can send me the relevant emails and we'll just provision those keys.
Sounds good. I'll do that.
Cool. So if you want to follow along, you will need to set your key in the Certora key environment variable and install Certora CLI, and then that should work. But if you haven't set that up already, then maybe just watch, and afterwards you can mess with that. Hopefully, it'll make some sense even if you're not able to actually use your fingers during this hour. Okay, so let's see if I can share the right thing here. Yeah, okay, so I'm James. I am the Chief of Technical Market Development. I have to remember that. And we're gonna talk about Certora's prover technology. I know Opyn has been using it, and we're excited to help all of you become deeper users of the tool on your own. So we're going to go through a simple contract as an example that's just sort of a simple bank account with a map that tracks the funds in each account, and also a storage field that tracks the total across all accounts. And this is fairly typical of a lot of contracts. And what we want to check for now is we're going to check several properties of this contract. But the first one I want to look at is just the deposit function. And we're going to basically, this is it's a good first kind of specification. It's a kind of specification where you say the same thing twice, once in code and once in math. And then you make sure that the code matches the math. And so in this case, we're going to check that the deposit increases the balance of the account by the correct amount. Okay. So let's
quick question. Should we ask questions at the end, or
no, you should ask questions all the time.
Okay, cool. So what is a property? So how do you all think about what are properties?
Whoa. I feel like I need to get my philosophy textbooks off the shelf here. What is a property? So
maybe better is like what is a good property? Like what is a good property?
That's an even harder That's an even harder question. Now I have to get my aesthetics books off the shelf. Okay, so what is a property and what is a good property? So, I mean, the boring answer is, at least from the Certora prover perspective, a property is something that you can write in a .spec file, but that doesn't really help you. You know, if you talk to verification people, they like to give lots of fancy names to different things. Like you'll hear them throw around the terms safety property or liveness property or specification or things like that. And they don't always mean the same thing, even when they use the same words. But for us, basically a property is going to be some kind of assertion, basically, that we can make about the behavior of the contract in a symbolic world. Okay, so in real life, when you deploy the contract, it's going to interact with the outside world. They're going to be sending it transactions. And we want to analyze the behavior of the contract in advance in all possible scenarios. Okay, so we're going to construct a symbolic world, basically, and then run the contract in symbolic land and see what it does and make assertions about its behavior. So that's going to be a property for us. What's a good property? A good property is one that helps you gain confidence in some aspect of your system that has consequences in the real world, right? So if we're doing this bank example and we don't want people to lose money, then maybe we want to check a property like this one that we're checking now, which is just checking that, you know, the deposit function works correctly. In a minute, we're going to look at some other properties that are maybe better than this one, but this is a good first example. Okay, good questions. let's look at this in code. So here's the contract. Fits on one screen. So like I said, we've got this mapping that has the balance of each account, and we've got this total that keeps track of the sum across all accounts. And then I only want to look at two functions. I want to look at deposit, and I want to look at get funds. Let's do get funds first. This is just a getter, right? So it takes the account, returns the funds, and deposit takes the amount that you want to deposit, and it deposits it into message.sender. Notice there's some weird stuff going on here, like where did this money come from? Like, shouldn't we be, I don't know, shouldn't it be like given to us? I don't know. It's a simple contract, right? It trusts the sender that if they call deposit, they really do have this money, and it's going to add it to the account. And this is the function we want to specify.
So it doesn't check like the message.values.
Right, exactly. Yeah, it's a bit of a strange bank, but it does, add things to funds.
Okay.
So let's write a rule.
It doesn't need to check message.values because it's more like an ERC20, right? Like there's
but like in an ERC20, wouldn't you have to justify somehow that you like had the funds or that you had bought them by like doing something else? Because the way this is written, anyone can call deposit at any time with any amount and add it to their balance. Right. So like there's no.
Yeah, because everyone has mint functionality,
Yeah. It's a race to the bottom. Exactly. Okay, but let's make sure we race correctly. So we're gonna write a rule. So this is I'm working in a spec file down here, and just like in a Solidity file we have contracts and we have functions. In a spec file we have rules. Okay, and rules are these symbolic worlds that I was talking about. So this specification language, I like to say it's kind of a strange programming language to come to as a programmer, because it's never intended to be run in any real sense, right? When you execute a specification, it doesn't run like a normal program. Okay, so what a specification does.
Why can't the specification language be what we write like smart contracts in, so that we don't have to like rewrite, or like so that like, or like why can't Solidity be written in such a way that doing formal verification on it is like easier? Or like why can't we build contracts in spec language basically? I don't know if that makes sense.
Okay, that was like 3 different questions. I think all of them were interesting. So why can't we write specs in Solidity? I think was maybe the first version. And why can't we write? And then the opposite was also a question. Why can't we write smart contracts in spec? That's also an interesting question. In principle, nothing's stopping you from trying to do that. I can tell you why we did it this way. So there are some features so like I said, the specification language doesn't run. Okay, it's a mathematical object that gets analyzed together with the contract, which means that there are things you can do in a specification that don't make sense if you ever plan to actually execute them in Solidity. For example, you can say uint amount, and this means let amount be a completely arbitrary 256-bit integer, right? And when I run this rule in the spec language, it's going to check it symbolically for all amounts. Okay, and that's something that doesn't really make sense to try to do if you were going to actually execute something, right? Because now you have to, like, I guess in principle you would iterate over all 2 to the 256 integers and try the rule. But that's not what the spec language is going to do. So it does symbolic things that don't make sense if you were to try to execute them. And there are things that just don't exist in Solidity that you want in specifications. So for example, we're going to look at an example in a minute where we pick like an arbitrary method from the public API of the contract. Or another example that we probably won't get to today are logical quantifiers like for all and exists. Those quantifiers don't exist in Solidity, but we want them in specifications. So basically there are symbolic features that you want. And because Solidity was not designed to do specification, it makes sense that those features are not there. You could imagine like extending the Solidity compiler maybe with those features, but that it's almost like a separate language. So yeah, that's the kind of trade-off there. I think over the long term, I think Certora is interested in designing maybe a smart contract language, maybe with better integration with the spec language, but we haven't gotten there yet. So for now, we're working on existing languages.
I have a quick question. Like, what's the difference between like writing my rule with Certora prover or just using like the SMT checker? Like other than like maybe Certora is more advanced than that.
Yeah, they're pretty similar.
Okay.
The SMT checker, it works on the source code level instead of the bytecode level. So the way the Certora prover works is it actually compiles the Solidity contract to EVM bytecode and then analyzes that bytecode against the specification, whereas the SMT checker never looks at the bytecode, it only looks at the Solidity source code. That has pros and cons both ways, right? So it's a more tractable verification problem to look at the source code because it's higher level, but you don't catch bugs in the compiler. And in fact, we find lots of bugs in the Solidity compiler by trying to verify the output and failing, and then debugging why it's failing and figuring out that actually it's wrong because the Solidity compiler has a bug. And you can't find those bugs with the SMT checker. But yeah, they're pretty similar, and they use very similar technology under the hood. And we are also based on an SMT solver. So in some sense, we are also an SMT checker. Okay, other questions?
Yes. So
Yeah.
you said, like in this rule, for example, you pass in UN 256.
Yeah.
One way of going about it is like iterating for every possible UN 256.
Mm-hmm.
But that's not what the Certora software is doing. So what is it doing?
What it's doing is it's taking the bytecode. So it compiles this contract into bytecode, and then it takes that bytecode and it takes this specification and it compiles those two things together into a system of logical constraints. Okay, so it's a logical formula. It's usually a very big logical formula.
So what might that look like?
Let's see, how can I answer that in a useful way? The logical formula, basically it encodes, like let's just focus on deposit for a second. Okay, so deposit, it starts in some world and it makes some change to that world. Okay, so let's play a little bit fast and loose here. Let's just say we want to do this in a logical formula. How would we do that? We would have a copy of the funds map in logic from the world before deposit ran. We'd have a copy of total funds from before deposit ran, and then we'd run deposit, and that would update the state. And in logic, there's no mutation, there's no updating the state. So that means we have new copies of the funds map and of total funds. So we basically have like funds underscore version 0 and funds underscore version 1 from after, and they would be related by the code of deposit, right? So the code of deposit says that the funds after is equal to the funds before, except in the key message.sender, it's incremented by amount. Okay, so we would say that in logic, and that would be the relationship between the two versions of funds, and similarly for total funds. Okay, so that's how you compile the code into logic. We haven't actually written the rule yet, but the rule is going to say basically that deposit adds the right amount. So it's going to say, now try to prove that funds of message sender is equal to the old version plus amount. And then it's going to ask a logic solver to solve that formula. Okay, so we basically compile the code into logic, compile the spec into logic, and make sure that the code implies the spec.
Okay.
I can give you some links. So this is a really old idea. So we didn't invent this, right? This is like a 1960s computer science idea. It's not a very well known idea outside the verification community, but it's old. So there's lots of good kind of tutorial material on that. I can send you some stuff. It's
Yeah,
pretty
I'd
cool.
love to learn more.
What exactly is the idea that's old? Is there something I can Google?
Yeah, it's called Hoare logic. I would Google Hoare logic. So there's a guy. His name is Tony Hoare, and he invented a thing called Hoare logic, which is a way to compile code into logic, basically. And this is also the same thing that invented pre and post conditions, which I'm sure you've heard of. So it's like kind of the fully formal logical version of pre and post conditions. Okay, I want to actually write a rule, so let's do that. Okay, so what are we trying to do here? We're trying to basically want to like let's write some pseudo rules here. We're gonna call deposit on this amount, and then assert that message.sender's balance increased by amount. Okay, that's what we want to do. So let's do that. So the way we call deposit is we say deposit, and we know we want going to pass in this amount. So it kind of looks like this. In Certora, in the Certora prover in the spec language, when you call a function in the contract, unless that function is pure or view, you need to pass in an environment. And what an environment is a symbolic representation of a bunch of kind of implicit variables in the EVM. So in EVM, you can get access to the current block number, you can get access to the current timestamp, you can get access to message.sender, you can get access to message.value. Those are all like implicitly, they're always available in scope. But in the Certora prover, we make that explicit. And that's useful because it means that you can say, like, for example, run these two functions in the same environment or run them in different environments. And you have the choice about how to say that. And we have to make it explicit in order to give you that choice. So here,
is that like payable or not?
Say that again.
Is that similar to function modifiers in Solidity or not really? Like or like some, not modifiers, but I mean like public, payable, these kinds of things.
Is what similar to that?
Like expressing a function scope, like, or context, or what would you call it?
Environment.
Environment. That was it. Yeah.
Yeah. Yes. So things like public and payable, they affect who can call the function. So that's one thing. I think the environment is a little bit different. It's really just trying to wrap up all of the basically all of the things that are secretly an input to every function without you having to do anything about it, right? Like message.sender is always there. Whether you say, like whether you use it or not, it's there. It's implicit. And so the environment is just here to make that explicit. So what we're going to say later is e.message.sender. So it basically says I want to get the message.sender from the environment e. Right, and so it's like it's a place to collect all of these implicit variables. Okay, so we always pass in an environment as like an additional first argument. Okay, so we said we're going to invoke deposit, and now we want to make this assertion that the message sender's balance increased by that amount, and we're going to use this get funds function to do that. So if we want to get the funds afterwards, we could say get funds e.message.sender. So this would be to get the balance of message.sender, basically. And in a rule, these function calls are sequenced just like they are in a normal program, right? So if you run deposit, it actually changes the world, right? It updates the account balances. So now if I get funds down here, I'm going to read the new value of e.message.sender's account. So if I want to compare that to the old value, I had better call get funds before deposit as well, right? Because otherwise it's been overwritten. I can't get to it anymore. Okay, so we're going to call it up here too, and better save our answer. So say like balance before is that, and just for symmetry, we can do it this way, balance after. After is that. And now we can make our assertion, which is that the balance after is equal to the balance before plus amount. Okay, and we'll give a little error message here. Deposited the wrong amount. Okay, so that's our assertion.
Do we need the environment variable in the getFunds function?
So because getFunds is a view function, we can actually use another feature of Certora to declare that getFunds doesn't need the environment. So you can set up your specification file to do that. I think I'm not going to do that because I'm going to screw it up and I'm going to confuse you. But yes, you can do that. It's called env free, and if you declare getFunds in the spec file to be env free, then you can leave this off. Okay, so if we so we have a rule now, we want to run it. So the way we run it is we come over here and we find this command line. And we come back over here and we paste it in. And then I changed the name of the spec. I called it live. Okay, so the way this command line works is Certora run is the thing that you're going to install with pip. And you give it the Solidity file to compile and the name of the contract in that file in case the file has multiple contracts. And then you say, I want to verify that contract that I just gave a name to against this specification file. Okay, so if we run that, it's going to go out to the cloud and start processing this. And I can go ahead and open this status window here. It says, it's working on it. And let me get myself back set up over here. So while that's running, let's think a little bit about, how could this possibly fail? I think one thing that's going to be that is kind of strange about this is that it's very tempting to think of these two languages as the same. And actually, from a design perspective, I don't know what the right answer is here as a language designer. Should we try to make the specification language as similar as possible to Solidity, or should we try to emphasize the fact that it's a different language? And I go back and forth about this like a couple times a day, whether we should be thinking of these as the same language or as different languages. And what you're going to see is that, in fact, this rule failed. Okay, so let's go look at why it failed. So if you click on why it failed, you get this report. So the red background and the thumbs down tells you that the deposit correct rule failed. If you click on the name of the rule, you get this backtrace basically. And if you drop these arrows down, you can kind of drill into what's happening. So the top of the backtrace is our rule. So remember what our rule looks like, right? It looks like a call to get funds, a call to deposit, followed by a call to get funds, followed by some assertion. Okay, so that's what we see in this trace. We see a call to get funds, a call to deposit, a call to get funds, and then presumably the assertion must have failed after that. So if we look at the local variables of the rule, we see that the balance before was 1. The balance after was 0. That's pretty strange. And if we look right here, we can see that in the argument to deposit correct.
Overflow.
Say that again?
Overflow.
Yeah, it overflowed. Okay. So now here's what's weird about it. Okay, so we all know that plus can overflow in Solidity. Everybody knows that. But what about this plus? Right? Like we just kind of wrote the same code twice we wrote it once in Solidity, we wrote it once in spec. So if this plus overflows, shouldn't this plus overflow and then we would get the same answer? Right? And the answer is no. And in fact, I claim it shouldn't give the same answer because we wouldn't have found this bug if it gave the same answer. Okay.
Wait,
so go ahead.
Yes, I do understand that. Yes.
So what that the conclusion of that means that this plus must be different, right? This is not solidity plus. This is mathematical plus. Okay, so that's why I say, sometimes it's useful to think of this like solidity, but other times it's not useful to think of it like solidity. And it's important that it's not solidity, right? It's important that it does something else. So here, this plus operates on arbitrary precision, unbounded mathematical integers. So when we say balance before plus amount, we're saying treat this 256-bit integer as if it was a mathematical integer without any range constraints. Similarly with amount, and then do this addition over the mathematical integers and compare it to this. Okay, and so that's why this rule is violated, right? Because balance before was 1, amount was the maximum 256-bit integer, which means that 1 plus that is going to go outside the range. It's going to equal 2 to the 256, right? And that's not equal to 0, which was the balance after. So that's why this rule failed. And if this plus had the same meaning in solidity, the rule wouldn't fail and we wouldn't have found this bug. Okay, so I think that's kind of interesting. You have to kind of keep in mind that this language wears several hats, and sometimes it doesn't do the same thing as solidity on purpose. So let's look at a fix to this.
Here's
Can I ask you a quick question?
Okay, a couple questions.
Oh, Mike, you want to go?
Yeah, I was just going to ask, like, when you declare this uint 256 as the input to your rule,
yeah,
is basically the sole purpose of that uint 256 to sort of like tag that quantity for when it gets plugged into functions that need a certain type, like you were saying that the plus is going to be on just like whatever arbitrary precision numbers. So like what is the purpose of the uint 256 when you declare it like that in the spec file?
Yeah, basically because this rule is about the deposit function, and the deposit function takes a uint 256. So like it doesn't really make sense, and it's just not possible for someone to submit a transaction to the blockchain that calls deposit on something besides a uint 256, right? Like you could try, but it'll revert. And so that's why I declared it this way. Is like I just wanted an arbitrary argument that made sense for deposit. One thing that's kind of strange about the spec language is that it implicitly allows you to convert these machine integers into mathematical integers, right? So when you do this plus operation, there's kind of an implicit conversion of these uint256 values into mathematical integers. But yeah.
Oh, interesting. I was thinking that the conversion was happening when you plug it into the deposit function, but you're saying that it's the opposite, sort of.
Yeah. Okay. Well, here's some real talk. The real talk is there's no conversion.
Okay.
Everything is actually a mathematical integer in the spec. And what uint256 means is that mathematical integer is constrained to be in the range 0 to 2 to the 256 minus 1.
I see.
Okay, and then what actually has to happen is that when we call a solidity function, we just have to make sure that solidity function is like, remember how I said we're compiling everything to logic? So when we compile that solidity function to logic, we just need to compile it in a way that like it expects a range constrained mathematical integer rather than like what it looks like it expects if you're a solidity programmer, which is a 256-bit machine integer. So that's kind of part of our translation process, is to convert this code into a logical formula that operates on range constrained mathematical integers. That's kind of a deep cut, but that's what's going on.
No, yeah, that's good.
That's really helpful. But this opens up to another question of how do you deal with floating point numbers?
We don't.
Wait, how do you what?
Floating point. How do you deal with floating point? That was
do you mean fixed point, or do you really mean floating point?
Well, fixed point, I guess.
Yeah, because I've never even seen a Solidity contract that used actual floating point, because the EVM doesn't have instructions for that, so it would be insane. But fixed point, right, is the idea of basically just taking an integer and multiplying it by a fixed denominator. So that works fine. You know, in some sense, like if you put your I am the EVM hat on and you think about how does the EVM think about contracts that use fixed point? It doesn't, right? It just treats them as integers, right? There's nothing special about the fact that this integer is being interpreted as some multiplied by some denominator. It just does integer arithmetic. And that's important because the EVM just doesn't have instructions for fixed point arithmetic. It has integer instructions. So you need to express your stuff in terms of integer instructions. And so because we work on the bytecode, you know, we don't have to know anything about fixed point because the EVM doesn't know anything about fixed point, right? So everything's going to be expressed in terms of integers. Now, where that gets tricky is when you want to write specs that make sense to you as a human on numbers that are fixed points. And then you need to figure out basically how to express that in terms of integer arithmetic.
Question: doesn't compound use floating point for something? Or maybe I'm just like.
No. Our V1 used floating point. V2 is all fixed point.
Well, okay. So, question that I have about like where did the 1 come from, right? Because you're calling balance before you're getting a get funds.
Yep.
On E, but E hasn't been initialized yet.
Okay, right. So remember I said this language doesn't run? So
I don't know if I followed that, what it means. Yeah.
Yeah, so in a normal language, if you don't initialize a variable, right, it's either an error or you read garbage or, you know, maybe you get 0 if you're in a nice language or something, right? In this language, if you don't initialize something, it means please analyze this specification under all possible values of this variable. Okay, so I said that that was what we were doing with amount, but that's actually also what we do with E. So please analyze this rule in all possible symbolic environments. So for all possible message.senders and for all possible states of the contract, for example, like, you know, we haven't constrained the funds map at all. We haven't constrained total funds at all. So it's going to analyze the contract in all possible storage scenarios, basically. And so when you look at this output and you see that it picked this particular amount, you know, all the maximum integer, and it picked these particular values, it didn't have to be that way, right? There are other counterexamples. There are other outputs that it could have given to reflect the same bug, right? For example, if we changed balance before to 2, then we could either leave amount the same or we could subtract 1 from amount. It doesn't matter. In either case, we'd still get overflow, right? So there are tons and tons of different like concrete values that the solver could have plugged in here. And it's just it's an implementation detail of the underlying logic solver that it, whatever side of the bed it woke up on today, it decided to pick 1 for balance before and max uint for amount. But it could have made other choices.
Is it deterministic?
That's what I was going to ask.
It's deterministic-ish, which I realize is not a super helpful answer. It's deterministic if you don't change anything in the input. And one of the things that you can, like if you make any change at all, it's all bets are off, right? So if I, like a silly example would be like reordering these lines, right? Doesn't have any effect on the meaning of the contract, but it affects the actual code. And I don't know, I've never tried this before, but let's just see what happens. Like, you know, I'm a little bit too familiar with the underlying logic constraint solver. And in my experience with this constraint solver, you change anything and you get a different answer. You might get a different answer.
Cool.
It just depends.
Wait, what did you just change the order about?
I just reordered these 2 lines.
Oh, okay. Yeah.
Right. It's just something that doesn't matter, but it does change like the formula that we end up sending. So I honestly don't know what this is going to do. I don't know if it's going to give us the same answer or a different answer. But my point is just that like I wouldn't really depend on things remaining the same. And even like, so the underlying constraint solver that we use the most is something called Z3.
Mm-hmm.
And like Z3 does a bunch of timing based stuff. Like it has all these strategies it tries where it's like, okay, for like 5 seconds, I'm going to try like doing this thing. And then if that doesn't work after 5 seconds, I'm going to come back and try this other thing. And so like, depending on like how loaded the cloud machine is at any given time, like that 5 seconds may or may not be enough to figure it out. And so like you can get non-determinism just in terms of like timing, basically, where if it happens to get lucky and finish it in 5 seconds, then you get one answer. But if it doesn't, then it has to try this other thing and it takes longer and you get a different answer. So yeah, it's really all kinds of bets are off. Let's see. So verification report. Cool, we got a different answer. So I feel
very cool.
Vindicated.
Yeah, nice.
So all we changed there was just the order of those 2 lines.
Oh my God, that's crazy.
So yeah, it's non-deterministic, and that also should convince you that it really is looking at all possible values, right? It's this huge space, and because there are many different examples that cause this rule to fail, it's just basically picking one that it happened to find first.
Well, it can't be all possible values. It's like many possible values.
All possible values.
But UN 256, you can't iterate across a UN 256. Like,
exactly right. So you better not iterate, because if you start iterating, you're never going to finish. So you got to do something else. So it does something else. It's like asking, you know, how is it that humans can do calculus? Calculus is about infinity. So we can never get to infinity. So how can we do calculus? And the answer is math, right? You can analyze situations without actually having to look at all the concrete examples. So the constraint solver is using the equations and the inequalities and all the things that we compile into the formula to solve the formula without having to just guess and check. Okay, cool. So let's look at, so we said the overflow was the problem. And, you know, if you've been around Solidity for a while, you know that this plus sign is just a bad idea. So we can look at a version of this contract that uses safe math. So we can write, you know, instead of copying Opyn Zeppelin, I just copied the few functions that I wanted. So, you know, we do the addition and then we make sure it didn't overflow. And then we can replace those lines we had before with calls to safe math. Okay, so we'll do safe add, and you can ignore this requirement here. It's for a later property. Okay, so if we want to check that, we can leave the rule the same because it still has a deposit function. It's still implementing the same interface. And all we have to do is change this to bank fixed and then let that run. So basically this is going to check that this contract satisfies the rule. And one interesting thing to think about is, you know, what happens in the real world if we pass in like max uint here for an account that's 1. Like, what does safe add do? I guess it reverts, right? So now as a specification person, you have to think, do I want to try to prove something about the case where this contract reverts, or do I only want to analyze the cases where it doesn't revert? Okay, so by default, if you just call a function, it assumes that that function does not revert. So if we want to, is that right? Am I saying that right?
That's right.
Okay.
Yeah.
So by default, this rule is not going to analyze the paths or the case where, for example, this addition overflowed. So if we wanted to prove something about that case, we would have to use another feature of Certora's prover of the specification language to do a special kind of invoke, a special kind of function call, basically, that does analyze reverting paths. So that's just something to keep in mind when you're thinking about what kind of specifications you write. I would say like 90% of the time, you don't have to really worry about reverting paths because they revert and they don't change the state. So like, at least they're not going to get you into like an invalid like contract state. The only thing you might want to prove about reverting paths in my mind would be like making sure that like it doesn't revert in cases you weren't expecting. So maybe we could, I don't really want to do this today, but we could try to prove a rule about deposit that says like, if deposit reverts, then one of these two additions had to overflow. Right, so those are the only reasons why deposit, or I guess this requirement could fail. And those are the only two reasons why you can revert.
Interesting. That's so cool. Would love to do that sometime.
Wait, so quickly, what's the difference between calling deposit and calling synvoke deposit?
There's no difference.
Oh, I see. That's what you're describing. That is
Yep.
the default.
Yeah.
I see. Okay.
So if you explicitly say invoke instead of sinvoke, so sinvoke is the default. If you say invoke, that means the S is for safe, which you can think of as. We also have new syntax. Thomas, what's our new fancy syntax? At.
You can put after, you can put at with revert or at no revert.
Like this?
If you want to be explicit either way. I don't remember if it's capitalized. I don't think it's capitalized.
With revert.
I can check.
Or no revert.
Mm-hmm.
Not sure. Yeah, I think it's better than sinvoke. We were just talking the other day about how, as language designers, we spend almost all of our time arguing about syntax and not anything that's important. But I think this syntax is nicer than invoke and sinvoke.
Yeah, those are right. I just checked.
Okay, cool. So yeah, so no revert or sinvoke is the default, and this version would check that has reverted. And there's also this variable called there's this like keyword inside of a specification called last reverted, which is a Boolean that tells you whether the previous call reverted or not. So you can use this to basically write that spec I was talking about. So you could say like last reverted, implies that like basically like one of the adds overflows. And like we'd have to think a little bit about how to express that in the spec, but like that's the basic idea of how you would prove that, or how you'd state that. Okay, so while we were talking about all that, our bank fixed job finished, and it verified. So that means that in all non-reverting scenarios, deposit adds the correct amount to the state. Okay. Cool. Okay, so I think we talked about how to run it. We talked about all of this. We talked about results. We talked about the fix. Okay, let's talk about another property. So another property we could try to prove of deposit, which is a little bit complementary, I guess, to the previous property, is that the total funds of all of the accounts in the contract is always greater than or equal to the fund of any particular user. Okay, this is a very strange property. I think no one who wasn't a verification person would ever come up with this property. I think, but the reason I like it is because it's got a relationship between multiple pieces of storage in the contract. So a lot of times in actual contracts, you have multiple storage slots that are related in some way, and you're maintaining some invariant of your contract that this relationship holds. So in the bank account contract that we've been looking at, maybe the most natural way to think about it is that the total funds is the sum over all accounts of that account's balance, right? Now, unfortunately, summation is an advanced feature. It's hard to express in logic, and so we're not going to do that today. So this property is my kind of using only straightforward features of the Certora prover, kind of something we can say that's kind of like that summation property, but doesn't require actually using summation. So let's take a look.
Why is this a weird property that like verifiers wouldn't think of?
Well, like, I don't know, if you told me, like, if you just asked me on the street, you show me this bank account contract, a totally normal thing to do. Just walk up to someone on the street and show them a Solidity contract and ask them.
I actually did that yesterday.
And you ask them, what's the relationship between, where are we? What's the relationship between this storage field and this mapping, right? Probably they wouldn't say that every like entry in this map is less than or equal to total funds. I mean, it's a true fact, but it's probably not what they'd come up with first, right? They'd probably say the summation thing first. So I just mean it's a weird property because it's like not the first thing that comes to mind if you were going to sit down and try to specify the relationship between these two slots. I don't know. It's not what I would come up with first.
Makes
Kind
sense.
of like incomplete proof too of.
Yeah, exactly. It doesn't kind of capture everything that's going on, but it's a start.
This makes it strictly better.
I think so. Yeah. But also a lot harder to state.
Wait, but the summation is a little total funds can overflow without like a single like entry overflowing. Right?
Can it?
Yeah. No. Same
I mean, in principle, you're right that like, if you allow me to just make up an arbitrary mapping here, I can construct a mapping such that there's no 256-bit integer that doesn't involve overflow that actually captures the sum of all of these. So that, in that sense, you're correct. But in terms of executions of the contract, none of those mappings are actually going to be reachable, right? There's no sequence of deposits you can make to reach a contract state where the mapping, like where total funds has overflowed, but the mapping hasn't, because we use safe add on total funds. So the first time you get to a deposit that causes total funds to overflow, it's just going to revert, and it's not going to let you deposit that amount. So it just prevents you from ever reaching a state of this mapping that is not representable, whose right. Sum is not representable. But yeah, you're right. I mean, like there are maps that overflow here, but you just can't get to them because we check. Okay. So let's write another rule. So I want to write a rule that corresponds to what we just looked at, and let's just check the deposit function again. So maybe we can, I don't know, start from here and see where it takes us. So let's call it deposit preserves our invariant. So our invariant is going to be.
The screen, I can't. The screen is not updating for me.
Sorry, I pressed the wrong button.
Okay. Okay.
I was still sharing the slides. My bad. Total funds. All I did was make a new file and copy paste our old rule and then rename it. And now I'm going to start editing it. So our invariant was that total funds is greater than or equal to the balance of one user. Okay, so let's get rid of all of this. Let's go back to the default. And now we want to do this. So we also, total funds is private, but we just manually named the getter here. So we can invoke the getter. So we have the balance after. We have the uint256. Yeah, if people have to leave, that's totally fine. We're recording, so you can catch up later. And I'm probably going to have to go in a few minutes anyway, so we'll be wrapping up fairly shortly. So let's get the total funds after. And now let's check that what were we supposed to check? Total funds is greater than or equal to balance. We'll say invariant violated. Okay, so now to run this, so let's keep running it on our fixed version. And now it's called sanity.spec. So give that a shot. couple things about how this is encoded. One thing is that the way we set it kind of in English was the balance of any particular user. But then the way we actually wrote it in the rule was to pick the user message.sender, which we didn't really need to do, right? We could have picked some other user. So maybe this rule is too specific in that sense. So maybe we should experiment with that. What else was I going to say about this? Can't remember. Well, let's just look at the report and see what happens. So it failed. Press the right button. Okay, so it failed. We can look at it. See what's happening here. So, okay, one thing is super strange. Amount, you can see amount is 0. So we tried to deposit 0. So we shouldn't have changed the state at all. And if we look at total funds, this is kind of strange, and I don't know. Oh, there it is. Total funds. Total funds is 0, but balance after is 1. Now, if balance after is 1 and we deposited 0, then the balance before, which we didn't actually get, must also have been 1, because deposit didn't change anything, right? Deposited 0, so nothing changed. We haven't actually changed the state of the contract. And the invariant was violated after we didn't change the state of the contract. So that means the invariant must have been violated before we changed the state of the contract. Okay, so we kind of screwed up in our rule here, because we're saying, starting in a completely arbitrary symbolic world, right, with no constraints whatsoever, does any invocation of deposit magically restore the invariant, even if it was false before? And the answer to that is no. Right? Deposit is not a.
Yeah.
Go ahead.
So is the right way to start is you assume that total funds equals greater than or equal to balance of one user a priori, and then no modifications can take you out of that state.
Exactly. So if we do this, and then instead of asserting, we can require. So we can require total funds before greater than or equal to balance before. And require, again, this is a case where, like, I don't know what the right language design trade-off is here, but I can tell you what we did. So we're going to reuse this keyword that you all know from Solidity, require, but it means something slightly different, right? Here it means assume. Okay, it means only analyze this rule in contexts where this constraint is true. So it's not asking the prover to prove this constraint. It's telling the prover to assume this constraint, right? Only analyze states where this is true. Now invoke deposit. Now check that that is still true. Okay, and this is how we would check the invariant. So we can rerun that. And so in general, this is a pretty common pattern for checking invariants, to basically assume it, then invoke something, and then assert it. And so we have various language constructs in the specification language to make that easier. And we can look at a couple of those. Other questions about this this rule? Okay. Pretty sure that's going to pass. Let me just show you, because I do kind of want to end on time-ish. Let me just show you one last spec. And it did pass, by the way. I just want to show you one last spec, which is how to do this on an arbitrary method. So in the previous version, it was specific to deposit, right? We basically said, assume the invariant, assume the invariant, call deposit, and then check the invariant. Okay, but there's nothing specific to deposit here, right? If this is really an invariant of the contract, then it should be preserved by all the methods of the contract. And so we have something called parametric rules, where you declare a variable whose type is called method, and all of the public functions of the contract will be plugged in here. So basically this rule is going to be checked for every public function, including deposit and withdraw and transfer. Okay. And there is a current limitation on the syntax where you actually have to say sinvoke or invoke here, but we have a fix to that coming soon. So soon you'll be able to just call f. But for now, you have to, if it's a parametric method, you have to use the invoke or sinvoke keyword. But other than that, it's the same. I didn't end up naming my variables, but I assume the invariant, I call the function, and then I assert the invariant. And the only other weird thing is that because we don't know what f is, we also don't know what kind of arguments it takes. And so we need this other feature, which we call data arg, which basically says, give me an arbitrary called like an arbitrary set of arguments, basically, that makes sense for whatever f you chose, and then call f on those arbitrary set of arguments. So I think we'll just end there. And I just wanted to show you this parametric rule, and we can pick it up some other time with lesson 2.
Oh my God, I really hope we can have a
Awesome.
lesson 2. This was awesome.
Yeah, this was super helpful. This was massively helpful.
Cool. Yeah, thanks.
This is super interesting. How can I learn more about like what's actually going on behind the scenes? Because I kind of, sort of, someone has once explained to me how formal verification works. It's basically like you're constructing, like, I'm not exactly sure. It's like some kind of NP complete problem that you're like using to express the code, and then you're like running that, but I'm not exactly sure like what exactly that means, and then like how it figures out what input violated that.
Yeah, so I really think of it as 2 steps. So first of all, I should say there's lots of different kinds of formal verification. So there's the Certora prover is based on a style of verification, like I said, called Hoare logic. And specifically like an automated form of Hoare logic, which is called weakest precondition generation, which basically, that's why I like to think of it as a compiler. So in this style of verification, it really is a compiler from code to logic. And it's interesting to look into kind of like how that compiler is written. Although I will warn you that if you talk to other people or read Wikipedia about Hoare logic, they probably are not going to call it a compiler. But I think it's useful to think of it as a compiler. So I can send you some links about that stuff. And then the second question is, once you have the logical formula, how do you solve it? And in the academic community on formal verification, we really treat these as 2 completely separate problems. The problem of, given a piece of code and a specification, how do you generate a logical formula that accurately encodes the correctness of the input? That's one problem. And the second problem is, given an arbitrary logical formula, how do you solve it? Okay. And there are people who work on one problem and not the other, and vice versa. But we need both. So the second problem, specifically the one that we're using, is called SMT solving. So solvers like Z3, they take these logical formulas as input. They don't care whether the formula was generated from a piece of code or whether it encodes a Sudoku puzzle or something else. It doesn't matter. They just solve logical formulas, and we use them basically off the shelf. So the question of like, how does it pick the number 1? If you wanted to understand like, why does Z3 pick 1 for that contract but 26 for the other contract where we just reorder 2 lines, to answer that would be a very deep dive into the source code of Z3 to figure out like, what kind of algorithms is it using, and why did it wake up on the side of the bed today that it picked 1? I would say like, I think it's probably best if I just like send by email some links about kind of the background of this stuff. But I would say like, this is probably not covered in most undergrad CS education curriculums, right?
Is
So
there like a grad level courses which
yeah,
explain this concept?
yeah, so at so I got my PhD at the University of Washington, and I know that we have a couple.
Hey, we have Mike as well. Got a PhD at UW.
Oh, cool.
Yeah.
So we have a couple grad courses that that cover this stuff, and I can link you to some slides and stuff like that. I also taught a class at UW last spring that was half about formal verification, and I have videos from all my lectures in that class, which I can also send to you.
I would love that. I would love.
Nice.
I would love that.
Are there also assignments that we could do?
Yeah, there are. In fact, I one of the assignments
Formally
was
verify Opyn.
Yeah, I haven't quite figured out yet how to convert my students into secret Certora workers. But the closest I've gotten is one of the assignments from that class was to implement your own verification tool. So it takes a little toy imperative language with assignment statements and global variables, and you implement the compiler from that language to logic, and then call Z3 on it to verify it. I will warn you that
That's so cool.
the assignments are a little bit open-ended, so but you can give it a shot.
Okay. Cool.
Yeah, I would love those. I found this quite easy to follow, so I would love to see more lectures of yours. That'd be great.
Cool. Yeah, I'll send those by email, and they can be distributed.
Cool. Yay! Thanks for teaching us.
Yeah,
thanks
this is
for
great.
coming.
Thanks so much.
All right.
Thanks, everyone.
Thank
Have
you.
a good weekend, or I guess it's
Bye,
Thursday. Have
all
a
of
good
you.
good day. Bye.
See ya.
Bye.
Thanks for coming, guys.